Okay, so intervals of increasing, decreasing. Now, I'm going to get you guys started on some of these here because I think it's important to get started on that. And we're actually going to look at that first question here, intervals of increasing, decreasing. So I'm going to write down that function here for you guys, okay? So we got 5 minus 3x squared plus x to the third power here. Okay, so here's our function. And we're going to start to explore something here. Let me find, I don't know, how come I can't find my mouse? Oh, there we are. Okay. We're going to start to talk about what this actually means. Okay, intervals of increasing and decreasing. So here's what I'm going to remark, first of all, by giving you some definitions here. It always starts with definitions. So we say a function is increasing if f of x1 is smaller than f of x2 for all x1 less than x2 in an interval in I. All right, so we're going to have to talk about what this means. And this is what we mean by an interval that's increasing. The function's increasing over the interval. And compare that to the following. We say a function, I'll call that f. F is, decreasing if we have the following. If f of x1 is larger than f of x2, for all x1 less than x2 in I. So I'm going to have to express what this means. Okay, you got decreasing and increasing function here. Okay, so I'm going to give you guys some time to write that down for a bit. These are definitions, and I think probably the important part is right in here. That you want f of x1 to be smaller than f of x2 whenever you have this situation there. And all this portion means over here, I'm going to write this down here, I'm going to put it in purple. All this portion means is you're going to walk left to right. Similarly, the other way. You're going to walk how? Left to right. All right, you guys okay with that? That's all that means. Now, if you said to me, can you draw me a picture? I'll draw you guys a picture here. I'm actually going to draw you guys two pictures. And I'm going to say, here's my A to B. I'll move B over here. Okay, so I have my interval A to B. Now remember, you need an x1 and you need an x2. They have to be smaller. In other words, right, we're saying x1 is less than x2. That's another way of saying we're walking left to right. So in other words, you're on this curve right here at x1. There you are. And then at x2, you're on the curve here. This value and this value, these are the y values, right? Because y equals f of x. So we say y is f of x. Here's what I'm saying to you. Okay? As you move left to right, what we say here is f of x1 is smaller than f of x2. You say, why? This is where f of x1 would be, and then here would be f of x2. Okay, I'm talking about here, here. In other words, the altitude is what bigger, right? The depth, think of it that way, or the depth of the altitude is bigger. That's what we mean. For every value in that interval, you have this situation. So actually, this is a picture, you know, and you want to remember, you want to think of it this way: this value and this value. And what do you have here? These two values here, right? So you're increasing, and all I'm saying is that the altitude is higher as you go to the right. So you're walking left to right. Remember that. You're walking left to right. So it's very simple. Are you going uphill? Say yes. This is an uphill situation. You know what that means? The function is increasing in what? Altitude or value. The y equals f of x. That's getting bigger. Okay, you with me on that? That's kind of a simple picture, a simple definition. So this is our increasing picture. What's the decreasing picture now? Okay, how are you guys walking again on this thing? Left to what? To right. Okay, x1 less than x2. What are the altitudes? This is y1, this is y2. Where are you higher, ladies and gentlemen? You're higher on the left than you are on the right, is that right? So as you walk left to right, this is going to be, what do we consider this? Downhill. This means your function is what? Decreasing. But what's really happening, really by definition, is f of x1 is bigger than f of x2. That's what's really happening. Okay, so you say, well, what about these other pictures? Draw these lines. All right, you guys okay with this? Now, here's going to be the next question. So you guys always want to know uphill, downhill. Here's the next question. How can we determine increasing and decreasing intervals? So if I just take a point on this curve, right? Let me go back here. Here's what I want to remark to you guys. I'm going to take any point on this curve. This is our increasing, interval from A to B, right? If I take a point and I draw the tangent line, see this tangent line? This is the key. In beginning algebra, what do you guys know about that tangent line? Yes, thank you. Good job. The slope of the tangent line is what? Positive, ladies and gentlemen. Absolutely. This is what I want you guys to see. Okay, that's the key here. The slope of the tangent line is what? Positive. That you're going to see that this means it's increasing. And then you say, give me an arbitrary point over here. Okay, here we are. Here's my tangent line. What do you know about this tangent line? Anybody know? The slope of that tangent line is what? It's negative. Okay? So I'm going to write that down. That when I put less than 0, that means the slope is negative. So it's a very, very, I should say, simple process in a way. The definition is simple. Increasing means you're going uphill on this, curve. Decreasing means you're going how? Downhill on the curve. Okay, you guys okay with that? All right. All right. So what does it mean here? First of all, I better make sure if I go back to that paper, I have the right one. Yeah, I do. All right. Right in here. Okay. All right. So here's what I mean. We're going to have to do what? This is code. This is code. Code for what? Finding intervals of increasing, decreasing. Sign analysis on the first what? Derivative. Okay, so if I said, okay, let's find the derivative here, right? Remember, you can replace this with y. So what is dy dx? Okay, you have to do this. 5 minus 3x squared plus x cubed. Do what? Properties here. You get what now? 0. What's this? 2x. What's this? 3x squared. So you get y prime to be what? Minus 6x plus what? 3x squared. Okay, so on a test, of course, I'm always looking for, can you get a derivative? All right, you guys okay with that? All right, now what do we say? How do we really answer this question? We said what? Sign analysis on that first derivative. So that brings me up to here. It's kind of interesting. I did have remember we discussed a little bit. Oh, apologize. Dry throat again, like always. I got my water somewhere. It's very sad to me in some ways, the state of what's going on with math education. Like even in summer, we're not going to offer 125, unless we can show data that says we can. So we're not going to do it, probably. I think they're scheduling that. So that means a lot of people are going to have some trouble. So here we go. Here's what 125. Where are we at? Yeah, 125. I'm going to keep my resources up. I'm going to look for it. It's right here. Nonlinear inequalities. I'm going to put this in here. This is sign analysis. This is a process, okay? We've done a little bit of it. I don't know if did I give you guys that for homework and say, hey, do that for homework? I don't remember. And then you have a video for that.
Okay, so
I
here
had
we go.
to talk to the student in 125 that he's not passing. And he's like really not passing, seriously not passing. Okay, but he's going to do some great things in STEM. Good for him. But, you know, he has some other issues, a lot of other issues. So I showed him the beginning algebra, you know, what to do here on my website, what he had to do to review, because what he has to do is review, you know, beginning algebra. So if you guys notice, I have even in beginning algebra a whole bunch of what? Videos, worksheets, blah, 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 right? I got all these resources there, even in that course. And yes, that's Mr. Judge. So you guys know these resources have been up for a little bit, a while. So that's more and more what the SATA is saying. They're saying everybody knows math already. Why are you trying to duplicate and make people go through this stuff again? Why are you torturing people twice or three times? You know, everybody already knows it. So if they're having trouble, just have them get tutoring. If they're having trouble, just have them look at some other resources. That's the state's answer. So the poor kid is like, well, I can't even take 125 in the summer again. No, nope. So remember that social justice, whatever that was, yesterday? We still have the flyers here. People getting paid 20 grand. Are you kidding me? You get it here for free. I get to tell you guys this stuff for free. Yeah. So here we go. So what I'm going to remark to you guys too, just like I remarked, we're looking at here in case people didn't see. I do have those resources. In case you guys didn't see, beginning algebra, all that stuff is there. I'm going to keep it up forever. I pay for it, by the way. It's not free for me. I pay for this website, and there you go. So here's the derivative and sign analysis. Now, if this was Math 125, you know, you probably start off with what we call descending order. So I'll write it as descending order. And remember the process. You say, what's this process? You have to find where that derivative is 0 or where the y prime does not exist. And you say, well, how do I do that? Well, it's a polynomial. So we say 3x squared minus 6x equals 0. Okay? And this is where the kind of the issues were, right? How do you guys solve for x? You guys know? You factor out the greatest common factor. That has to be GCF, and then this is times a quotient. Okay, so 3 and 6, the GCF is 3. X squared and x, the GCF is x. So it's always x to the smallest power. Do you guys remember that? Now, what's the quotient going to be? X minus 2. So we actually did that worksheet, algebra, every calculus student should. It's the same process, you know. It's the same process. Okay, now what do you guys use? You guys remember? You have to use the what? Got to use that zero product rule. And what's the zero product rule going to be? 3x is 0. X minus 2 is 0. So this means x, this is 0 divided by 3. And you're going to add 2 to both sides. Maybe you guys want to see that. Right? So you get now x is going to be what? 2. Okay? 0 divided by 3 is 0. So you have x is 0 here. So here you go. Now, why aren't you going to check? This is checking where the derivative is 0. Why don't you check that does not exist? Anybody know? Why does this not make any sense? It doesn't make any sense. Does anybody know why? You don't have a fraction, right? You don't have a denominator. Is that right? This is a nice polynomial. They're differentiable everywhere. All real numbers are differentiable. So sign analysis, ladies and gentlemen, is a great tool. And remember, we have to find where x is 0 and x is 2. This is, again, that derivative. Your derivative is 0. Your derivative is 0 here. Region 1, region 2, region number 3. Easy breezy lemon squeezy. Does anybody know what you guys do next? Remember, this is where the derivative was 0. What do you guys do next with this? Anybody know? What do you do next? You have to pick a what? A t. We got to pick a what? A t. We got to pick a t in every interval. What does t stand for? Test point. So you have a test point, ladies and gentlemen, -1, +1. You got to pick a point in the region. It can't be where it equals 0. You got to pick a point in each region. So a number to the left of 0 is -1. What else is to the left of 0? In other words, I'm saying, what if you focus on this region here, region 1? What could you use as a test point? Do you guys remember? -2, -3, -4. You guys okay with that? What else can you use? -5. What about region 2? What can you use? 1 is clearly in that region. So is 1 and 1/2. You guys see what I'm saying? You need a test point clearly in the region. And then finally at the end over here, I guess I'm going to use gold. You need a test point in region what? 3. Any number like 3, 4, 5, 6, and so on. Okay, do you guys remember the process? Now, what do you guys do now? Do you guys remember? What do you do now here? You're going to have to find the sign of that derivative. What I like is the fact that 3x, x minus 2. That's the same function. You guys okay with that? Why do I actually use the factored version? You guys know why I use the factored version? Because it's easier with the arithmetic. It's a lot easier. Because I'm going to have to plug in a test point now, okay? I get to plug in -1 and -1, and what do I get? Is that -3, -1 minus 2? Isn't this what? -3 times, what's a negative times a negative? I don't even care about the number. I just care about the what? Sign, because this is called sign analysis. Now, what that means is you tested region 1. That means region 1 is a what? Has a positive derivative. Now, what does that mean about region 1? If the derivative was positive, I'm going to put this line here. What is that line? That's an increasing slope because I have a positive M tangent. M tangent's positive in region 1. Okay, you guys okay with that? Sign analysis. Okay, what about region 2? What do I plug in for region 2? T is 1. What does that mean now? We have what? 3 times -1. Isn't that -3? So what do we know about the derivative here in region 2? It's negative. Decreasing what? slope. So in region 2, your function's what? Decreasing, because the test point is negative. All right, what about region 3, ladies and gentlemen? Four, what's that derivative? 3 times 4 is what? 12. What's 4 minus 2? So y prime will be 24. Is that right? So if it's 24, what's the deal? It's an increasing slope. This is a positive number. It's increasing. Now, what you guys are looking at is gold. Okay? You're looking at a lot of things, in all honesty. I'm going to erase this. Okay, remember, what's our function? This is the function. Okay, so what's our conclusion? You guys want to see the conclusion? Here's the conclusion here. How do we describe this answer? Right? Your function is increasing on what interval? F is what? Decreasing on what interval? Okay? What region do you have a positive derivative? Because that's the increasing region. Right? Your function's increasing on that interval. What is that interval? Do you guys know? That's from negative infinity up to 0. Be careful here. Why don't I include 0? Because 0 is not positive, it's not negative. Okay, you guys okay with that? 0 is positive. Now, where else is it positive? 2 to what? Infinity. Okay, why don't I include 2? Do you guys know why I don't include 2? Because at 2, the derivative equals 0. It's not positive. 0 is not positive. Check your checking account balance. Hopefully it's positive. If it's 0, not happy. But there's worse situations. It could be what? Negative. Anybody have that situation? I hate to say it feels horrible. You guys haven't had that situation? Good. You feel horrible. That means you got to make money just to get to 0. Just to be broke. It's like you need to make money to be broke. Isn't that horrible? All right. Now, where is the derivative negative? Because that's where you have the interval decreasing. Between what? 0 and 2. So, ladies and gentlemen, there you go. A picture is worth a what? 1,000 words. Okay, you guys okay with that? Now, this is a nice, beautiful polynomial. Polynomial functions are nice because they are defined everywhere. In fact, they're continuous everywhere. What I mean by that is they're continuous for all real numbers. So what you have now here, ladies and gentlemen, is the following. Tell me, I'm going to ask you this question here. Do you have horizontal tangents? What do I mean by horizontal tangents? Do you have them? Where do you have a horizontal tangent? You guys remember? When the first derivative is 0. Right up in here. Where's your first derivative 0? When x is 0 and x is 2. Isn't that where you have the... So in other words, you say, x is 0, x is 2. What's your y values? Right? You know your y values? Plug in 0. 5 minus what? 3 times 0 squared plus 0 cubed. Y is what? 5, so I have 0, 5. HT, horizontal tangent. What about the other? Do some arithmetic. Okay, what do you guys get here? Is it 1? What did I do? What did I do? Oh, 2. Ah. I guess it helps to have some good vision, right? Would you say y was? 1. Okay, I'm going to say y is 1. You guys could do the arithmetic. So what's this location? X is 2, y is 1. You're going to have horizontal tangents there. All right, you guys okay with that? Easy breezy lemon squeezy. Okay, I'm going to go to Desmos now. 5 minus 3x squared plus x cubed. You guys know I like to save red for other things. So here we go. Now, notice this. Verify that point and verify that point. You guys see these points? 0, 5, and you see 0, 1, or 2, 1. This is how we describe the uphill situation walking left to right. So, sure enough, we can verify that we're going uphill. Is that true? And then once we get to the top, we have a horizontal tangent. And then what do? You're going downhill, and then when you get to the valley, you have another horizontal tangent. Is that right? Then when you get higher, you're going increasing again forever. So we're verifying the analysis that we just did. But does anybody see anything here, anything that's additional? Anybody see anything that's additional here by any chance? You might see something here. At 0, 5, aren't you at top of a hill? What does it mean you're at the top of a hill? What does that mean? You're at a max. Good, a relative max. What if you're in a valley at 2, 1? What does that mean? Well, you're in a valley. You're at 2, 1. Is that right? Easy breezy, lemon squeezy? So here's what I want you guys to know here. There's something called the first derivative test. And I'm going to just summarize it here. You're going to say, let C be a critical value for a function here. Then you have the following. Question 1. If f prime changes from positive to negative at C, okay, then f has a local max at C. That's question 1. Question 2, if f prime changes from negative to what? Positive at C, then what's the story? Then f has a local min at C. So this reveals where you have a local max and where you have a local min. Okay, and you're changing. You say, changes how? Positive to negative, or if it changes negative to positive. That's the first derivative. And what this statement is, it's called the first derivative test. Every calculus book has that written down, but it's really what I just shared with you guys here. So what I mean here is you are standing at the top of a hill over here, and then you are standing over here in a what? In a valley. So does that kind of make sense? If you say, if I'm on top of a hill, I know I have a what? This is location of a relative what? Max. You're in a valley. That's where you're at a relative what? Min. Okay, I want you guys to highlight this here. Relative max, relative min, relative max, relative min. Easy breezy, lemon squeezy. So this picture is worth a what? 1,000 words. So you might say, okay, what's the relative max? Go back to the function. You know what your function is? What's your function? Right here. It happens where x is 0 and x is 2. Remember this function here? It happens when x is, what do we say? X is 0. So that means y is 5. You already found it. A relative min happens when x is, what's the other value? 2? Happens when x is 2. What do you get here? You get 1. There it is, ladies and gentlemen. That's what they're going to ask you in these questions. They're going to ask you for intervals of increasing, decreasing, and then they're going to ask you for what? Where's the relative max, relative min? And what is the relative max, relative min? There it is. So what's the key? Remember what I just said? Sign analysis on the what? First derivative answers a lot of questions about the curve, about the graph. So that's where we're at. Easy breezy, lemon squeezy. We're going to try these things here. Okay, so if we go again and look at that worksheet, we're on 115. We don't want to be there. We're going to go to 261, right? I'm going to try to scroll in here if I can. Let's scroll in. Okay, let's do this next one here. Is that x squared over what? X squared plus 3? Double check, because you guys know I can't really see. This is what? X squared. Is that x squared plus 3? Double check. All right. So we're going to have to do the same analysis. Okay, so notice this here. I'm going to go to Desmos. It's crazy. Okay, I'm going to change the function. This is the picture. So if you look at this picture and you're walking left to right, just looking at the picture, because don't you guys have some homework questions that kind of look like that too? Right? I'm going to talk about, so in other words, you're going how here? Downhill. And then you get to a minimum value, you're in a valley, and then you go what? Uphill forever. You see what I'm saying? Are you ever on top of a hill? Say no, we're never on top of a hill. So let's see what sign analysis can verify for us. Okay? So we need the first derivative. Let's get that there. What rule do we use? Quotient what? Rule. We square the denominator. What do you have up here? X squared plus 3. Right, we've got to use quotient rule. Okay, are you guys good with derivatives? Hopefully. Okay, let's see. What do you get here? 2x. What do we get here? 2x. Is that right? Notice we're not even using chain rule here. Now we get what? 2x cubed plus 6x minus 2x cubed. Everything over x squared plus 3 squared. Okay. Do you guys know what happens with that 2x cubed? Cancels. We have 6x over x squared plus 3 squared. Okay. What do we notice, ladies and gentlemen? You have a what? You have a quotient. Is that right? So because you have a quotient, you're going to find what? You're really finding those critical values. Okay? You say, what do you mean? You're trying to find when y prime is 0 or when y prime does not exist. What does that now mean? 6x is 0 or x is what? 0. 0 divided by 6 is 0, right? So I got a critical value. And then, what do you have? X squared plus 3 squared is 0. What does that mean? X squared plus 3 is 0. Didn't we see something like this yesterday? Anybody know what I'm going to say? What am I going to say about this? Right? This is the numerator equals 0. That's where you have a derivative equal to 0. And then the denominator equal to 0. This is where you have it does not exist. What did we see yesterday? What do we say? This never what happens. I mean, it happens, but it's a complex solution. And we're not dealing with complex calculus. It does exist. Okay? So this is only one critical value for us. That happens when x is 0 here. Okay? Now, I want you guys to note, this is going to be important for us. What's the domain of the function? Input values. What's your domain? Do you guys know what the domain is? All real numbers. How do we know it's all real numbers? You guys remember how to find the domain? How do you do that? You set the denominator equal to 0. You say, what do you mean? Can you solve for x? No, you don't have any horizontal asymptotes. Horizontal asymptotes happen where the denominator equals 0. So you don't have any. Because again, you get complex solutions. So what does that mean? There's no horizontal asymptotes. That means the function is defined everywhere. All real numbers meaning everywhere, okay? So that's important. You say, why do I care about that fact? Because when you do your sign analysis, you're going to see with some questions, you're going to have a region that's to the left of 0. Region 1, region 2, this is where that derivative is 0 here. Okay, so give me a test point to the left of 0. -1. Give me a test point to the right of 0. Oh, +2. We're going to test some regions. Okay, you're going to test the first derivative. What's the first derivative again? See why this is important? So like on a test, ladies and gentlemen, you're going to get credit for what? The first derivative. And then you're going to get credit for all the rest. So if I plug in -1, the first test point, you get -6 over 16. Is that true? What do you think I mean by this? I don't care what the answer is. I just care that the derivative is what? Negative. Okay? So we have a decreasing what? Slope. Plug in now +1. What happens when you do that? Isn't 6 times 1 6? 1 squared plus 3, isn't that 4? 4 squared 16. This is positive. So ladies and gentlemen, here's the deal. Region 2 is what? Positive. Okay, you guys okay with that? Okay. Okay, so that means, let's do our analysis here. Your function is what? Isn't it decreasing on what interval? -50 to 0. And your function is increasing. How is it increasing? You guys know? On 0 to infinity. Is that true? Did you guys see that there by sign analysis? Now, are you standing here at a hill or a valley? I know it's a horizontal tangent, but you're standing in a what? In a valley. Is that right? You're switching from negative to positive. So in other words, you have a relative what? Min only. The function is at 0, whatever that is, because it happens with this x value. X is 0, you got the derivative of 0. So plug that in your function. You got to know the original function, though. Okay, so if I plug that in here for y, don't I get 0 squared plus 3. Isn't 0 divided by 3 0, by the way? So you say, what does that mean? It means you have a relative min at what? At 0. So they're going to ask you these kinds of what? Questions, okay? These are coming. I'd say get started ASAP. Those are coming. It's kind of one of the reasons why I kind of jumped to this a little bit. so I can get started a little earlier. But we're going to talk about the mean value theorem over an interval and stuff like that too. So anyway, so there you go, ladies and gentlemen. It's another beautiful example. Yes. Well, good question. The definition of a relative minimum value is really the y value. So we're answering it right here by saying, hey, the relative min is 0. If I go to Desmos, they're saying, what is the minimum value of your function? It's 0. And notice to the left is 0, and you're walking left to right. Is that decreasing? Say what? Yes. And as you go to the right of 0, are you going uphill? Yes. Notice you're never, though, at the top of a hill, are you? You're just going up forever. Same thing over here. This goes up. I mean, this is coming down, in all honesty, as you go left to right. And it goes down to 0 and then goes back up forever, sort of. I don't even know. It actually goes up to 1. We'll see that in the future. So, ladies and gentlemen, it's a good question, relative min. But you're going to look at the sign analysis on that first derivative. That's pretty much what you do. Easy breezy, lemon squeezy, hopefully. So then, number 3, everybody's favorite. Y equals cosine squared x minus 2 sine x. And they're nice enough to give us a what? A restricted what? Domain. Okay? Now, I'm going to look at Desmos now. Okay? Just to share with you guys really what that will look like. Cosine squared minus 2 sine squared. Cosine squared minus 2 sine squared. Right, okay. Or it's not minus 2 sine. It's minus 2 sine, I think. Get rid of that. Now, what was the interval again? Go with this. So I'm going to just remark here, right? You're not seeing Desmos. I apologize. So here's the function in Desmos over that interval from 0 to 2 pi. Notice I have, I'm at a valley at pi over 2. Is that true? And then what am I at 3 pi over 2? I'm at a what? Hill. You guys okay with that? And so as you walk left to right, I'm decreasing from 0 to pi over 2. Then I'm increasing from pi over 2 to 3 pi over 2. Then I'm decreasing back from 3 pi over 2 to 2 pi. So think of going uphill, downhill as you're walking left to right. Okay? So this is going to describe our increasing, decreasing. Now, of course, what do? We have to do the what? Yep. Y prime d dx cosine squared minus what? 2 sine x. You know what this derivative is going to be? What's this derivative? 2 cosine x, what? Sine x. What's this derivative? What's the derivative of sine? Derivative of sine is what? Cosine. Okay? So y prime will be 2 cosine x sine x minus 2 what? cosine x. So you say, what do I do here? You have to use sign analysis on that first derivative. So there's a trig function. So you're going to try to find where that equals 0. You say, why? Well, they're nice and continuous functions defined everywhere. Huh? Let's see. Derivative of cosine is minus sine. That's right. Okay. Minus 2, derivative of sine is cosine. Okay. So what I'll do here is this. I want you guys to notice. What can you do? You're going to factor out what? Negative 2 cosine. If you do, you got sine plus 1. Is that right? You guys okay with this? Double check my algebra. I'm factoring out what? The minus 2 cosine. There it is. I'm left with sine plus 1. Now what am I going to do? I'm going to use the zero product rule. That means negative 2 cosine x is 0. Cosine x is 0. This is sine x plus 1 is 0. And I get sine x is negative 1. So what does that actually mean here? When is cosine 0? Do you guys know? When x is pi over 2, and when x is what? 3 pi over 2. When is sine negative 1? And when x is what? 3 pi over 2. Is that true? So remember what I said about this restricted domain and everything, right? You're going to do sign analysis now. You say at pi over 2, the derivative is 0. At 3 pi over 2, your derivative is 0 here. Okay? Now, I restricted the domain from 0 to what? From 0 to 2 pi here. Is that true? So what I'm saying, go back to the original function. This is the restricted domain I'm referring to. That's important to know. It goes from x is 0 to 2 pi. So we're just going to look at x from what? 0 to 2 pi. Okay? So I need a test point in each one of these what? Regions. Region 1, region 2, region 3. What is in region 1? 90 degrees. What's less than 90 degrees? That's what I would use, pi over 4. And then what's between 90 and 270? 180? I would use pi. And then what is between 3 pi over 2 and 2 pi? That's 270 degrees and 360. Anybody know? What's 5 pi over 4? I don't think that works. What's what? What's 7 pi over 4? 7 times 45, what is that? 315? I think that works. So these are all my what? Test points. What am I testing again? I'm testing the what? The first derivative. Always use the factored version. So if I'm going to use pi over 4, do you guys know what cosine of pi over 4 is? That's square root of 2 over 2. Do you You guys know what sine of pi over 4 is? Same thing. What's square root of 2 over 2? Isn't that 0.7? So this would be 0.7. And this would be what? 0.7. What's the point? I don't care about the answer. I care about the sign. Negative 2 times 0.7 is negative. And then 0.7 plus 1 is 1.7. The point I'm making is that this is a negative what? It's a negative decreasing between 0 and pi over 2. What are we going to test now? Region 2. How do we test region 2? Plug in pi. What's cosine of pi? Sine of pi is 0, is that right? Cosine pi is negative 1. So I get a negative times a negative will be a positive, and 0 plus 1 is 1. Here's my point. Negative times a negative is what? Positive. There you go. Increasing. Easy breezy lemon squeezy. Now, what about 7 pi over 4? What do you guys think is going to happen here with 7 pi over 4? Well, what is cosine of 7 pi over 4? What quadrant is 7 pi over 4 in? Do you remember? You're going to say, Mr. Judge, we're already seeing that's about 0.7, right? Sine also is about 0.7, but this is quadrant what? Quadrant 4. All students take what? Calculus. So what does that mean? Cosine's positive, but sine is what? Negative. Is that true? In quadrant 4? Okay. So cosine is positive 0.7. And then what is sine? Is negative 0.7. Okay. So a positive times a negative, there's going to be negative. 0.7 plus 1 is positive. Sure enough, region 3 is what? Negative, decreasing slope. Put your person here. You're in a valley. Here you're at the top of a hill. So what can we say about this? A picture is worth what? Not 1,000 words, but 10,000 words. So here's your conclusion. F is what? Decreasing on what interval? 0 to pi over 2 union d pi over 2 to 2 pi. F is increasing. Where is it increasing at? Pi over 2 to what? 3 pi over 2. Where are you standing at in a valley? All right, do you guys know? Yeah, at pi over 2. So relative min is the value of the function at pi over 2. Aren't you in a valley right in here? This is what I'm saying. That's a relative minimum value. Over here, you're at the top of a hill. This is a relative what? Relative max, and it happens at 3 pi over 2. So relative max happens when the function is 3 pi over 2. So you're going to have to go back to the original function, not the derivative. Go back here. You have to plug in both pi over 2 and what? Well, pi over 2 is 90 degrees. Is that true? Cosine 90, I think this one's 0. 0 squared is 0. Sine 90 is 1, so this will equal negative 2. So, in other words, when it's 90 degrees, we get a negative 2 value here. Okay, you can check 270, but I'm going to check my favorite Desmos. Because I want you guys to, this is 90 degrees, and sure enough, we are at what, if you can see this? We're at negative 2. Isn't that the minimum altitude? And then where are you at up here? 3 pi over 2 is going to give you positive 2. So that's the relative what? Max. And of course, you're decreasing in quadrant 1, increasing quadrant 2, decreasing quadrant. Oh, let me say that again, not quadrant. Should really share with you guys the idea. X equals this is what I want to share with you guys what you really did with sign analysis. I mean, region 1, 2, and 3. Region 1 has a negative derivative. Region 2 has a positive derivative. Is that right? And region 3 has a negative derivative because you're going downhill. This is what we're saying. Negative, positive, what? Negative. So that's kind of like a rough sketch. And isn't this equal to a positive 2, ladies and gentlemen? You see what I'm saying? Beautiful, beautiful, beautiful. And of course, we now have what? You got these 4. I want to continue. Maybe I shouldn't, at least continue for a little while. I'm going to place that there. All righty. So, okay, good morning to all of you here. Good morning, Ruben. Good morning, Dihal. Good morning, Oscar. Leilani, good morning. Good morning to all of you guys. Good morning, everybody here. So let's get to work. What I'm going to say here now is number 4, okay? What's number 4 here? This function is what? 200 plus. Now, I can't see very well. Old man judge. So hopefully you guys can see this here, okay? So I'm going to get to a couple of these because they're actually really good. Okay, number 4. So ladies and gentlemen, we're going to find intervals of increasing, decreasing. This is part of the work we did. And I'm going to say this here. Remember what we have to do. This is all code for what? Sign analysis on the first derivative. But if you're looking at a polynomial function, okay, this is a polynomial function. You never have for polynomials derivatives that do not exist, okay? So what you're going to find here is critical values first. And that's fine by taking the derivative and set it equal to 0. So we're going to differentiate this function. So we can call this y. 200 plus 8x cubed plus x to the 4th power now, okay? So I'm going to use my properties here. So let's do some derivatives. What's this going to be? 0, what's this? 3x squared, what's this? 4x cubed. So y prime becomes 24x squared plus 4x cubed. Okay, you guys okay with that one? Does that look okay? Now remember, you say if you're finding critical values, it's a polynomial function, so you let this equal to 0. Okay, that's going to get our critical values. Now, we have to solve this for x, right? Now, what you're going to see a lot of times with this is you're going to have to factor out the greatest common factor. All right, you guys okay with that? Okay, so you have to factor out the greatest common factor. So what's the greatest common factor of 24 and 4? Because you have to do this separately with the numbers. Does anybody know what's your GCF? 4. Good. And then you say, what about the GCF of x squared and x cubed? It's always x to the what? Smallest power, okay, for the GCF. So your GCF here is 4x squared, okay? So remember, we got to find that quotient. So how do you find this quotient here? Anybody remember, you take the original and you divide by, what's this? 4x squared. Doesn't that give you the quotient? So you take 4x squared over 24x squared over 4x squared plus 4x cubed over what? 4x squared, that's your quotient. You end up with 6 plus what? X. Okay? 6 plus x, or x plus 6. So this is how we get this quotient. Remember, you want to do that algebra that I shared with you guys before. That's vital. Without it, you can't find an answer here. Okay, without factoring out that greatest common factor, you can't answer this question. So I'm going to put this here and just remind people we factored out the greatest common factor. There's the technique. Now, remember what we do with this. What's it called? The zero what? Product rule. So what's the zero product rule? Do you guys know? This is going to be what? 4x squared is 0. 6 plus x is 0. Set them both equal to 0. So divide both sides by 4. I get x squared is 0 over 4, which is 4. Now this just means x is 0, ladies and gentlemen. So we have a critical value. Subtract 6. You guys know, what do we get here? Negative 6. Okay? Now remember something about these critical values here. In order to really be a critical value, they have to be the domain. They have to be in the domain. Domain of the original function. This original function is a polynomial function. What do you guys know about the domain of all polynomials? You know what it's all real numbers. Yeah, everything works. So polynomials are beautiful functions. When you graph them, they're these rolling hills. If you guys remember from Math 260, they're rolling hills. They're smooth. There it is. Okay, so we know this is all real numbers. Now you say, well, they want us to know about intervals of increasing, decreasing. So we go through sign analysis. Negative 6 is to the left of 0, and this is a sign analysis on that first derivative. So we put the zeros here, right? Remember something here. This is region 1, region 2, and region 3. Okay, you guys okay with that? Now, what do you guys always need here? Right, for signing out, you need test points for each region. So give me a number to the left of negative 6. What do you guys think? Any number, this is what I mean, has to be to the left of what? Negative 6. We could call it test point. That'll test region 1. Right? So give me a number. What number? Negative what? Okay, that'll work. Is that right? It's good. It's a test point. Good job. Okay. So let's look at region here, 2. Give me a number between negative 6 and 0. What's a test point? Any number? -1 will work. Good. Okay, now give me a number to the right of 0 for this last region, region 3. Okay, and I'm going to color coordinate this. What number? Maybe +1. I'll choose that one. How's that? So notice, what are we testing again? The signs on the first derivative. Okay, so we have to get the first derivative. I'm going to say to you, it's right here, but it's y. I'll copy. Okay. Now, I always use the derivative that's factored because it makes the arithmetic easy. Or I should say it makes it easier, right? So it's easier arithmetic. So if I plug in now, -7, what do you get here? 4 times -7 squared, 6 minus 7. Do you guys know a little secret here? I don't even care what the answer is, okay? All I care is about the sign, all right? So I know -7 squared will give me a positive number. I don't even know what that is. I don't care. But 6 minus 7 is negative. Is that right? So here's my point. Region 1 is what? Negative. And if it's negative, we have a what? Decreasing slope. Do the same thing now with what number? -1. So we get what? 4 times -1 squared, and then 6 minus 1. Again, do I care that -1 squared is positive? In a sense, I don't know the number. It's positive. But I do know 6 minus 1 is also what? So region 2, what do we know? Positive, ladies and gentlemen. Okay? So I want you guys to know, there you guys go with that, okay? Testing each region. And we have a positive slope, then that's uphill. So, sometimes these numbers are really easy to use. Now I'm going to use +1. That becomes 6 what? +1. Is that positive? 1 squared's positive. Is that right? Let me be careful here. Okay. Is that true? What happened here? X is -6. X is 0. So we're going to test region number 3. And we get, is it 6 plus X? Okay. I don't know. Double check, ladies and gentlemen. Am I doing everything okay? You guys okay with that? What do we notice here? Looks like region 3 is also what? Positive. So check to see if everything I did is okay here. Okay, let me get a glass of water. Looks okay to me. Okay, let me look at this function here. 200 plus 8x cubed plus x to the 4th. Sorry. Okay, this is kind of a... Sorry. Let me see if I can stretch this out because it's hard. Let me see if I can graph it so you guys can see here. I know the x-axis should be if I do -4 to +4. That's a little better, okay? And I want you guys to see something. Well, it's wow, look at this way down here. What do we know? At -6, we have a what? It's a horizontal tangent, but you're standing in a valley. We got a minimum value. Is that right? And then we're going to say, I'm going to share with you guys this here, because you say, well, what happens at this point? Something happens special there too. At 0, what's the deal? You're not standing on a hill. You're standing on a cliff. Does that make some sense? You're not on a hill, are you? Because around you, you're not at the highest point. To the left you are, but not to the right. So this is what I call the cliff situation. Like you're on a cliff. Think of this as mountains. So this makes a lot of sense. Let's draw our conclusion here, okay? This is the conclusion. Again, the picture is worth 1,000 words. We've seen this here yesterday. Here's what we say. Our function is what? Decreasing. What interval? -infinity up to -6. Okay? Right in this interval right here. That's what I just described. How do I know the function is decreasing there? The negative first derivative. And then, what do you say here? This is something as well. The function is increasing. Where is that function increasing now? It's where that derivative is what? Positive. Is that true? So what interval is that derivative positive? -6 to 0, union 0 to infinity. Be very careful, ladies and gentlemen, because this is where you have the positive first derivative here. Okay, I want you guys to see that here. Don't say from -6 to infinity. Why? Because at 0, the derivative is 0. 0 is not positive. Okay, 0 is not negative. 0 is neutral. So you said, if you stand at this point, that's called a what? You have a what? A local min at y of -6. You're having that local min at this value. That's the really, -6 is not the local min. The local min is that I have to plug in what? -6 for y. Okay, and now you can also call it f of. Okay, f of -6. So I got to go back to what the y value is, and I go, oh, I got to plug in -6. I got to plug in what? -6 here. You guys can see that here, right? So I'm going to use my TI, because I had it open for trig, and I'll say 200 plus 8 times what? -6. And that's raised to the third power. So I need my caret key. Okay. Come out here and then do what? Plus -6. Close that. Raised to what power? 4. There you go. And so that's -200 and what? 32. Okay? So to kind of bring this back here, it's -232. And what do we call this? A local what? Min. Is there a local max? Say no. You say, but Mr. Judge, I'm standing over here. And I'll tell you, you're not standing on top of a hill. You're standing at a cliff. Okay? You're standing at a cliff here. extremely important detail. And I'm going to say something here because this is important. Recall this function here, because if we remember, we have this function x cubed. This is the classic cliff question in my mind, in a very fundamental way. You're standing at a cliff. Okay? You say a cliff when x is 0. So if you find that derivative, isn't that 3x squared? And finding where that critical value is, we got a critical value. This means x squared is 0 because 0 divided by 3, right? That means x is 0. So if you did your sign analysis now, you only have 2 regions. Give me a test value to the what? To the left. Give me a test value to the right. Plug in 1, you get a positive value. Plug in -1, you square it, you get a what? Positive value. Increasing slope, increasing slope. You're at the cliff. This is a classic example that we mentioned in the past. You could get a critical value, but just because you get a critical value does not mean it's a relative max or min. Okay? It's no guarantee. If it has it, it'll happen at a critical value. This doesn't have a relative max and relative min. So I want to emphasize this. There's no relative max or relative min. Okay? This is something that people will make a mistake at. They think just because you have a critical value, it guarantees. No, it's backwards. Remember the if-then? Let me express this if-then. Maybe you guys understand an if-then this way, right? Well, maybe I remember my classic example, if what? Anybody ever been in a relationship? If what? If you're nice to me, then I will love you forever. Does that happen, ladies and gentlemen? First of all, that conditional is not a valid statement. But it's a statement that can be used like anywhere. So conditionals are not valid in general, but in math they are. So if we prove them, they're valid. If, then. So if you say, if you're nice to me, then I'll love you forever. Okay? That's the same statement here. If you have a relative max, then what will happen? It'll happen at a critical value. But the backward statement is not valid. If you have a critical value, that doesn't mean it happens that doesn't mean you have a relative max or relative min. This is the example of it. So you say, if you're nice to me, then I'll love you forever. Okay. But just because you got love forever doesn't mean the person was what? Nice to you. Okay, you can't say it backwards. Anyway, whatever. Sorry. A little bit of relationship advice. Take a look. Sure enough, aren't you at a cliff at 0? So just because you have a critical value doesn't mean you're going to have a relative max or a relative min. It's backwards. If you have a relative max or min, then it will happen at a critical value. So you can have a cliff. So you say, what does that really look like? Well, look at sign analysis. You have to look at sign analysis. Sign analysis will tell you if you have a cliff. It'll tell you if you have a relative max, relative min. It's only when you change these slopes right here. Okay, so here, this is what we call the what? The cliff. All right, you're at a cliff there. If it's negative and negative, you're also at a cliff. All right, so good. You guys learning something here today, maybe? What number was that one? 4. Geez, who made these? Let's do number 5. You might say, why do I have to see 5? You have to see different examples. Why is x squared minus 1, that's going to be cubed now, okay? Now, one of the reasons I like looking at these is because What do you guys notice? It's still sign analysis on the first derivative, okay? What's your first derivative? Exactly. You see, does chain rule go away, ladies and gentlemen? It doesn't go away, does it? So what's this derivative? 3 x squared minus 1 squared times the derivative of x squared minus 1. What's that derivative? Okay. So put it all together. 3 times 2x gives you what? 6x. X squared minus 1 squared. Okay, you guys okay with that? Not too bad. Now, remember, what you're looking at, if you say I have to do sign analysis, you're looking at another polynomial. So you're not going to try to find where that derivative does not exist. This is a polynomial. They're nice, beautiful, smooth curves. That's the thing about polynomials. They're like the most beautiful curves in a way. Okay? Smooth. In other words, there's no corners. Rolling hills. Think of rolling hills. So when you do sign analysis, you set that derivative equal to 0, right? So you have 6x. X squared minus 1 squared equals 0. Sign analysis says this. 6x is 0. Divide by 6, x is 0. X squared minus 1 squared is 0. But you guys know that means, that implies what you have here must be 0. And then this, x squared minus 1 and 0 means what? X squared is 1, and x will be plus or minus square root of 1. Or that means x is plus or minus 1. Those are two answers. X is positive 1, negative 1. Notice, do you need, well, notice, what are these again? CVs, critical values. So the homework you had to do on critical values is valuable. Right? You got to do that algebra. You got to do these derivatives. But this is the first time we have seen what? Yeah, what do we see now? We have what? Negative 1, 0, 1. This is where your derivatives are 0. This is the first time we've seen how many what? 1, yeah, 4 regions. 0, 1, negative 1. That's going to give you 4 regions here. Negative 2. Isn't that to the left? Okay, I'm going to use positive 2. Just for symmetry, I'm going to use negative 1/2. I'll use positive 1/2. There you go. We got to find the signs of these regions. And we got to find it for that first derivative right in here. Okay, you guys ready for that? We're going to plug in what? Negative 2. Notice something here for x. If I plug in negative 2, 6 times negative 2, isn't that negative? And if I square negative 2 over here, I get 4, and then 4 minus 1 is 3, and I square 3. In other words, it's not going to matter what I put in here. It's going to be positive. So you guys know that x squared minus 1, parentheses squared will always give you a positive answer, but this means that this region is negative here. Okay? Decreasing slope for your tangent line. Compare that to if you put positive 2. Notice again, positive here, positive here. This is positive if I did it this way. I know I'm going out of order. But since I had 2, I'm going to do that, okay? So let's test now region number 2, negative 1/2. Over here, negative 1/2 squared is 1/4, minus 1 is negative, but I'm squaring that. So this is always positive. But now 6 times what here? Negative 1/2 is negative. So that means I have a negative region number what, 2? Okay. I got the cliff situation there because that negative, negative, right? Now use positive 1/2. What happens with positive 1/2? Again, over here, if I use positive 1/2 because I'm squaring here, I'm going to have a positive number again. But this time, 6 times positive 1/2 is a positive number. Is that right? So what I have here is region 3 is going to be what? Positive. And there you go. There it is. So I'm going to clean this up. Let's answer this. What's your conclusion here? F is what? Decreasing on what intervals? And F is increasing on what intervals? Right, where is it actually decreasing? We got to be careful. Yeah. It's this region with this region. Don't include negative 1. Right? It's from negative infinity up to negative 1 union negative 1 up to 0. So even if I change these colors, make sure you guys understand this is region 1 and this is region 2. You unite them. Don't include negative 1. At negative 1, it's 0. You're at a cliff at negative 1. Positive with what? Positive. So over here, what are you going to have? 0 to 1, union 1 to infinity. In what? Creasing. Okay, you guys okay with that? Do you have any relative max, relative min questions? What do you guys notice about this? Any hills and valleys? You're in a what there? Aren't you in a valley? How do you know you're in a valley? Because you have decreasing to increasing. Going to be in a valley. So you say, what does that mean? You have a relative min equal to f of what? 0. So go back to your f function. You plug in what here? 0. So you get 0 squared minus 1 cubed. Minus 1 cubed is negative 1. Okay? Just plugging in 0 there gives you the value negative 1. So f of 0 becomes negative 1. What is the relative min? It's negative 1. It's not 0. It's what? Negative 1. So what's this curve? Because you say, oh, x squared minus 1 cubed. So I say Desmos y equals parentheses x squared minus 1. And what do you do with that? you cube it. Okay, so let me take a look at this. This is the curve, okay? At -1, you're not in a valley, are you? You're kind of in a cliff. +1, you're not in a valley, you're in a cliff. Let me say it again, sorry. You're not on top of a hill at -1 or +1. You're not on hills, you're in cliffs. 0, you're at a minimum. So sure enough, doesn't the curve verify the analysis that we're doing? Okay, you guys see what I'm saying? This curve verifies your analysis, so there you go. Pretty good stuff. We're seeing some new examples. What do you guys think? So is it good to go over this today, you guys think? It's a good idea to wake up, get out of bed, and crawl on over here to campus, you know? Got a nice warm bed and get out of that bed. You guys know what I mean? I don't think people want to get out of bed. What do you guys think? I'm going to send you guys a survey. So you guys sign up for a face-to-face class, and, you know, I mean, I don't know, maybe you guys like, you know, people are different. Maybe people like, do you guys like the flexibility? Just wondering. You like that flexibility? Why do you like it? All right, good. You know, because I had a student. She had me in the pandemic, and she got an A. You know, she had an A in 125, and then she had an A in 227. But the difference was we were coming back to campus. Like, she had me in 125 in spring of whatever year that was. I don't know what year it is we came back. I don't even know what year we're in now. You know, so that was remote. She got an A. And then she was concerned. She goes, "Mr. Judge, I'm taking you for 227, right? But it's face to face." She goes, "Are you still going to record the lectures?" And I didn't even consider that. I was like, "Huh?" I go, "What do you mean?" I go, "Well, I don't know." And she told me, she goes, "Because I think I would have failed the class if you didn't record the lectures." And I said, "What? How could you fail?" For some people, what's the deal? They got to go back and take a look. They got to make sure, right? So that helped her tremendously. So, okay, I got a bunch of hard drives crashing, filling up space because I'm recording the lectures and blah, 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 and you put them upload, you know. But if it's helpful, then great. That's I think the whole idea. Okay? That's my opinion. Anyway, a nice little break from sign analysis. Now we get to get back. Okay, I want to remark about this question. This is an interesting one too, because like I said, I'm glad we're starting to talk about some of these here. I want you guys to focus on this. What's your domain? The second you have a what? Square root. Remember, your domain only works. You can't have complex numbers. So what happens is whatever's under the radical, you set that greater than or equal to 0 because you need that to be either 0 or positive. So the domain here, ladies and gentlemen, is numbers that are greater than or equal to 0. That's going to be of interest to us when we do our sign analysis on the first derivative, okay? You're going to see what I mean. So y prime d dx x minus 4 x to the 1/2 And remember, what did I say about this derivative? Doesn't that always show up? X to the 1/2 shows up, so that's 1 over 2 squared of x. And then what's this derivative? This is going to be what? 1. So 1 minus 4, 2 squared of x. It's 1 minus 2 over what? Squared of x. So I'm glad we're going over these. Okay, you guys okay with this one? Now, here's what I want to remark about this. You might say, what do I do here now, right? Because remember, when we set this equal to 0 to solve, we got to simplify this. Or I should say, we have to not simplify, we have to subtract. And what do you guys notice when you subtract a whole number with a fraction, right? Replace that whole number with a fraction that has the same denominator. So you want the square root of x over the square root of x, okay? Does that make some sense? So now you have the square root of x, square root of x, 2 square root of x. Okay? And Leilani has a great question. Is there a difference between calling it local or relative? No, Leilani. They're the same meaning. They're the same exact meaning. So whether you want to call it local or relative, it means the same thing. Okay? So sometimes, you interchange, hey, local max, relative max, because different books, they call it local max, they call it relative max, whatever, it's the same thing. So, if I'm doing it inadvertently, I apologize. So, I don't know. What have I been doing here? Relative. So, I'm using the word relative, but it's the same. Local and relative are the same. Now, we have a fraction here, okay? So, I'm going to color this orange, and I'm going to color this green. If you remember what I've been doing here, remember critical values? It's where that derivative is 0 or where the derivative what? Does not exist. Now we're going to have a does not exist situation. That does not exist, right? You set the fraction. It's when the denominator is 0. So that means x is 0 squared. So x is 0. So at 0, ladies and gentlemen, the derivative does not exist. But where is the derivative equal to 0? Well, the square root of x minus 2, that numerator has to be 0, which means the square root of x is 2, which means x is 2 squared, or we say x is 4. So at 4, the derivative equals 0, because your derivative is a fraction. So even looking for these points is all a part of your sign analysis procedure here. So we have at 0 and 4. So at 0, derivative does not exist. At 4, that derivative is 0. So we're notating some very important attributes with this first derivative. Okay, you guys okay with that? So far, so good? All right, you guys okay with that? All right, what comes next? If you're awake, well, you might say, wow, I got region 1, region 2, region 3. Is that true? Is that right? You guys think, is that okay? Or maybe that's not okay. I'm going to have to throw out region 1. Does anybody know why I throw it out? Why do I have to throw out region 1? It's like, don't even bother with region 1. You only have 2 regions. Why does that go away? The domain is what? Remember this domain? I said that's going to be an issue for us. This function is only defined for positive numbers or 0. Because of that square root, ladies and gentlemen. So throw that out. Now, I'm sorry, not -2. I'm going to say positive. I'm going to use +2 test point. I'm going to use +9 test point. Two and 9. Where's the function? Right here. So when you plug in a what? 2, plug in a 2. Oops, apologize. We're testing the derivative. Where is it? Right here. I got the wrong one. So when you're plugging what in here? A 2 and a 2. Isn't the denominator positive? Do you guys know what the square root of 2 is? It's about 1.4. So in the denominator, it's positive, but in the numerator, it's 1.4 minus 2. What does that give you? It's negative. Decreasing slope. Okay? X is 2. Now change this. And X will be what? 9. Square root of 9 is 3. That's positive, so it's 3 minus 2. So my numerator is 3 minus 2, which is 1. Ladies and gentlemen, you got a positive slope. There we go. Okay. All right, let's answer a question here. Let's do the conclusion here. So you can see some more work here. Here's your conclusion. What's the story? What do we say? The function f is what? Where is f decreasing? 0 to 4? Negative slope. Is that true? F is what? Where's f increasing? Is that 4 to infinity? Is that true? What are you? If you're standing over here, what are you standing on? Okay, you're in a valley, so it means we have a relative or local relative min at y of 4. Now that's, or f of 4. Y of 4, f of 4 doesn't matter. Okay? So go back to that y, and you say plug in what here? 4. So I get 4 now minus 4. What's the square root of 2? 4 minus 8 is negative 4 here. So you get negative 4. Okay, you guys okay with that? And that's pretty much all the analysis you can do. It only has the relative min. There's no local what? Don't do this. There's no relative or local max. You don't have to say that. Only if they ask. Is there a local max or relative max? There's none. Yes. So same thing there, Lilani. You got that as well there, okay? All right. So this is the analysis you guys do with sign analysis. A lot of questions are done this way. I also want to remark, let's see if we have x minus 4 square root of x, right? You might say, what does that look like? This is what the curve looks like. it's decreasing from 0 to 4, and then it's increasing from 4 to infinity. So at 4, the smallest value of the function is negative 4. I think if I do a range here for y, I could say 10, negative 10, negative 10. What did I do? Yeah, you see it a lot better. Okay, hopefully you guys see that a lot better. What do you guys think? And notice, is the function defined for negative values? Nope. Okay, you guys okay with that? Isn't that beautiful? I don't know about you guys. Six. Seven. F of x. X to 2/3 minus x. Let's find the derivative. Okay. So I hope you guys did some work on derivatives. What's this? 2/3 x. What's 2/3 minus 1? Negative 1/3. What's this? 1. Okay, you guys remember this? Some of this here. There's your constant 2. And then x to the minus 1/3, that's 1 over x to the 1/3, which is the cube root of x. So you're going to have to take a fraction again, subtract a whole number. Cube root of x, cube root of x. You might say why? Because you got to have the same denominator. Okay, you guys remember that? And there you go. Now, remember, if you're going to find a critical value where that y prime is 0 or where the y prime what? Does not exist. So 2 minus the cube root of x is 0. And over here, we say the cube root of x is 0. Okay? This one and this one. That's what I'm looking at. Because you have a rational. You have a fraction. Okay? So this is gonna, if I add the cube root of x to both sides, now x will be 2 cube, so x will be 8, okay? And over here, the same thing, cube root of x, this means x is 0 cube, or simply x is 0. Okay, so let's kind of remember what this stuff means. If we go to the function, what's the domain here? It's all real numbers. Why? You might say, but isn't this going to be, right? You have a cube root here. This is like x to the, this is x squared, but you have a cube root here. Okay, right in here. x could be any real number because you could take the cube root of negatives, you could take the cube root of positives, right? So it's all real numbers. So you say, why is that important to know? Because when you look at sign analysis here, we truly have now 3 regions. It's not like the last problem. Okay, got to be careful. At 0, this does not exist. Right, this is for the first derivative. But like the last problem, we threw out a region, not now. We don't throw it out. So you take a test point to the left, like -1. You take a test point to the right, maybe like 2. And a test point over here, maybe like 9. I don't know. But you're testing that first derivative, that you're testing this. And I might even do the following, right? Because if I know I'm testing this, I'm going to put it back. I'm going to copy it. Yeah, anyway. Okay. Well, it's not going to work out nicely. I might use this. This is what I'm saying. I might use like 27. Say, that's crazy. You're going to go all the way to 27. There's a reason. You know why there's a reason? Reason 3? Anyway, let's test region 1. If you plug in -1, what's the story? Do you guys know the cube root of -1 is -1? This thing? So this is 2 minus a minus. This is 2 plus 1 divided by -1. 3 over -1. Okay. I don't care about the answer. I just say region 1 is negative. What happens when I plug in the 2? Anybody know the cube root of 2? What's 2 minus the cube root of 2? See, the cube root of 2, I don't even care about the answer, really. Because it's positive, but I do care about the 2 minus the cube root of 2. I wonder what that is. I'm going to go to my calculator without thinking about it. 2 minus cube root of 2. I guess I'm going to have to put 2 raised to the 1/3 power. Okay? I don't care about the answer. What do I care about? The sign. So, ladies and gentlemen, the numerator is positive. The denominator is positive. Region 2 is positive. Oh, I'm standing where? I have a relative min. Or do I? We'll talk about that. What about 27 now? You guys know what the cube root of 27 is? Isn't that 3? So 2 minus 3 is negative. I don't care about the denominator because it's positive, but I have a negative over a positive. And sure enough, I'm standing where? I'm standing on a hill. So since the domain is all real numbers here, that means every real number gives me an output. Okay, just because I'm not differentiable at 0 doesn't mean I'm not defined at 0. The domain's all real numbers. Okay, I'll go through that analysis here for you guys. I'll share with you my point. What's the conclusion? F is decreasing. Where is F decreasing? From negative infinity up to 0, union 8 to infinity. So I might need some space. So negative infinity up to 0, and then 8 to infinity. So your function is decreasing. F is what? Increasing on what interval? 0 to 8. Okay? So you have a relative max. I mean, let's start with a relative min at f of 0, okay? Now you say, but Mr. Judge, the derivative doesn't exist at 0. And I'll say, I know it doesn't exist. There's a lot of flavors of does not exist for the derivative. The function is defined at 0. How do I know the function is defined at 0? If I plug in 0, doesn't this just give me 0 minus 0, which equals 0? Your domain is all real numbers. Okay, so you go, well, how does this really work? Well, you have the value of the function defined at 0, even though it's not differentiable there. We're going to see what that is. I'm going to remind you guys. You have a relative max, though. Where? F of what number? 8? So you're on top of a hill. Remember this relative max at 8? Go back to the function. You got to plug in what now? 8 here. Okay? So notice what you get. You get what? What is 8 to the 2/3? It's a cubed of 8, what? Squared, 2 squared. And you're right, it's 4. So this is 4, ladies and gentlemen, this final answer. Okay, all the work I know, you say, I can't see where that is. Neither can I. It's over here. Okay. Oh, I'm sorry. That's not the answer. That's what? 3 times 4 minus what? 8. That's 12 minus 8. 4 again. Weird. So it is 4. Sorry. So it has a relative maximum value at 4 because you're on top of a hill. That's the relative max. So you go, oh, I'm on a hill at 8. The altitude is 4. And then at 0, my altitude is 0. Okay, you guys with me on this one? You guys see what I'm saying? So let's see what Desmos says. You can see this. 3x to the 2/3 minus x. So here's my point to you, ladies and gentlemen. This is one of my most favorite examples. Okay? It has all these nice, important locations. It doesn't like, oh, it does do the 0, 0. Remember what we said at the origin? What do we say there? If it's not differentiable, there's a lot of, there's 3 reasons why. It could be you have a vertical asymptote. That's not happening here. You don't have a vertical asymptote. It's not a rational function. It means you can have a vertical tangent line. Well, that's not vertical, straight up and down. What's the last situation of does not exist? You have a corner. Is that a corner at the origin? We also say it's not smooth. It's not like a polynomial. So being not being differentiable has meaning for us. The function's still defined at 0. It's just not differentiable at 0. You got a corner. And you got the relative max at what? X is 4. Okay, you see what I'm saying? So I hope you guys enjoyed an additional day of what? Of sign analysis on the first derivative and what it all means. And you could look at the graph again and say, hey, we're decreasing on that interval, and then we're increasing, and then we're decreasing. There you guys go. Okay, now I give you guys homework because sometimes people will say, hey, where's my